Superconductors can carry electricity without resistance, so they're more efficient than normal copper wires. However, these materials have to be cooled to a very low temperature, known as a transition temperature, before electrical resistance disappears. Developing superconductors with higher transition temperatures is one of physics' greatest quests. Recently, scientists found that subjecting certain materials to extreme pressure can produce higher transition temperatures. Now, researchers at the Carnegie Institution's Geophysical laboratory with colleagues have unexpectedly found that the transition temperature in a three-layered bismuth oxide crystal, referred to as Bi 2223, exhibits rising transition temperatures at two different pressures. They believe this unusual two-step phenomenon comes from competition of electronic behavior in different kinds of copper-oxygen layers in the crystal. Bi 2223 is like a layered cake. On the top and bottom are insulating bismuth oxide layers. On the inside of those come layers of strontium oxide. Next are layers of copper oxide, then calcium, and finally the middle is another copper oxide layer. Interestingly, the outermost and inner layers of copper oxide have different physical properties, resulting in an imbalance of electric charge between the layers. The scientists doped the material with charged particles, which also helps raise the transition temperature, and then subjected it to pressures up to 359,000 times air pressure at sea level, the highest pressure obtained for this material. They found that the transition temperature went up at pressures beginning at 100,666 atmospheres. But after that, more pressure ended up with lower transition temperatures. The reduction of the transition temperature stopped at 237,000 atmospheres, and at 359,000 atmospheres, the transition temperature rose again. The researchers think that 237,000 atmospheres might be a critical point where pressure suppresses one behavior and enhances superconductivity in layers that exhibit different properties. The findings may offer a promising way of designing and engineering superconductors with much higher transition temperatures. The research was supported by the U.S. Department of Energy, Carnegie, Canada, and the National Natural Science Foundation of China. It's published in the August 19, 2010 issue of Nature. This is John Strom for the Carnegie Institution.